So Annex 71 is a research project from the International Energy Agency, the Energy in Buildings and Communities program, or within the Energy in Buildings and Communities program. So it's an international collaboration. You see here all the institutes, all the countries involved, mainly European countries which are involved now. And we are looking at building energy performance assessment based on on-site measurements. And I don't have to go in detail all the background. You know all the challenges we are confronted with, climate change, CO2 reduction, etc. And this led to a strong restriction of all the energy that we can use in buildings. So this is an example of, for the Flemish government, the evolution of the E level that is imposed by the government. You see the orange bars give the reduction, stepwise reduction as imposed by the government. And you see in blue, that's the average value that we get nowadays based on the building permits. And that's a little bit a tricky thing. So it seems that we are performing extremely good. Huh? We have this severe reduction, but even then we do much, much better than what is required. But all this is a very theoretical approach. What we do, we have our building plans and specifications, we have the building delivery, and then we label our buildings based on what we designed here, based on a very simple calculation method that we use to say how good these buildings are. And most of the time they seem to be very good, on paper at least. Actually, what we see is that the real performance is often much worse than the design performance. And in that way, we miss a lot of opportunities to optimize our energy consumption. We perform much worse, actually, than what we do in our labeling. So that's a performance gap. This term has been used already quite a lot today. Looking at the performance gap means we look at the difference between designed energy performance versus actual energy performance. If we can disaggregate this performance gap in three parts, that's the building itself, and then we mainly look to the building fabric. We look at the building services, and we look at the users of the building. And in a previous project, I will just show it, we have been looking mainly at the performance gap of the building fabric. And what you see here is a comparison of predicted heat loss coefficient of buildings, or dwellings, and the measured heat loss coefficient of buildings. And you see that if you're talking about a performance gap, most of the time we are not talking about a few percentage mismatch, but in this case, you see that the overall heat loss coefficient of the building, wow, none of the buildings has a lower heat loss coefficient than the predicted one. That's the first. And sometimes we have difference up to 100% and even more than that. So this performance gap just on the building fabric is actually rather huge. So today there's no real operational rating. Actually, our rating is based on the design, and we have little measurement-based optimization of buildings. Actually, we design a building, and we've seen a lot of examples already today, and then later on we use the buildings and we assume that they perform as they were designed and that we don't have to interfere anymore. At the same time, we see a lot of trends. We have Internet of Things, we have home automation systems. You can keep track of the temperature in your living room on your smartphone. You can keep track of the energy consumption, but that's all what we do. We actually don't use this to optimize our buildings. And we collect more and more data on energy consumption. But again, there's hardly much done with this data. So the question in this research project is, to what extent can we use this actually on-board monitored data to assess the energy performance of our buildings? And if we can assess it, then we can also improve them. So that's the idea of the Annex 71 project, building energy performance assessment based on in-situ measurements. And it's a rather theoretical approach. It means we are people from statistical background, building physical background, where we combine this research field. And what we do is we try to develop methodologies which are able to characterize and assess, and we make a difference between both, the actual energy performance of buildings buildings in use and based on the onboard monitor data. In the project, we restrict to dwellings, but both on an individual dwelling scale as well on building districts or large apartment buildings, etc. And we make a distinction between two kinds of methods where we'll use the data for. On the one hand, we have what we call characterization methods. On the other hand, we have what we call quality assurance methods. So the first one, what we actually do is we use the data just to build simplified models, which are able to simulate the behavior of our building and our users and our systems. And these simplified models we can use, for instance, to optimize smart grids. We can use them to optimize the control of a solar shading device, etc. So this is in engineering what we call system identification. Based on the input-output data, we identify the system, and if we can identify the system, then we can optimize it. On the right hand, that's more quality assessment. So what we try to do is, based on the data of the building in use, we try to pinpoint some of the key performance indicators that we also try to catch in our EPBD regulation. So things are the overall heat loss coefficient, the efficiency of a heating system, also solar aperture, this kind of things. We call that physical parameter identification. What's the major outcome of the project? What are we aiming for is actually a kind of matrix where we have on the x-axis the quality and interpreted as the cost of the data, which can go from very rough to very detailed. In the previous presentation, we saw an example of how many, 7 kilometers, or I don't know anymore, of cables. Then we are really here at the right end of the x-axis. On the y-axis, we have the requested accuracy of the outcome, which could be we want a very high accuracy or a very low accuracy. And we look for statistical methods which are able, for a certain quality of data, what kind of accuracy do we get from the output. So look at it, for instance, if we want to determine the heat loss coefficient of a building, what kind of data do we need for the statistical method to get an output, and with what kind of accuracy do we get then this output. And the aim is not to end up with a building with 7 kilometers of cables and sensors included in it. The aim is actually to cover the whole field. Why do we want to cover the whole field? Because for some aspects of some performance indicators, it can be important to have a very high accuracy. If you think at quality assurance of a heat loss coefficient, it could be that indeed, if, as a government, I would say, okay, I would like to have the heat loss coefficient with an uncertainty of 1 or 2 watts per Kelvin. But for other performance indicators, it could be that I'm already very happy with a rough estimate. If I'm a social housing company, I would like to know which of the houses now I have to renovate as in a first step. Then I can get a first grip on the heat loss coefficient, and I don't need it that precise. I probably, with very rough data, it gives me already a view on what do I have now as a building stock and where do I have to interfere the first. I will show you some first explorative results. 2 dwellings from the UK. One is a newly built houses in Gainsborough, and the left is 2 typically English houses, more than 100-year-old, in Loughborough. And we look both at, as said, the system identification and then the quality assurance. So we asked, based on the measured data of the buildings in use, we asked people to develop a model, a simple model, to predict indoor temperature. That's, can we model our building based on the input-output data that we have? And for the quality assurance, we asked to calculate the overall heat transfer coefficient. And I will focus on the latter. So we look at what's the overall heat loss coefficient of a building, and it's a very simple theoretically thing. We can easily calculate the overall heat loss coefficient of a building, but it's much more complicated to get it out from real in-use data, because people are disturbing the thing all the time. They're opening windows and doors. They are using all kind of things in the house. At the same time, you have outside boundary conditions, rain, solar, radiation, etc., etc. So it's a very dynamic system. We get a very complex, and the equation is a little bit changed a little bit, but I will not go in detail on the equation. Just to tell you that somewhere in this equation there is hidden something that is related to the heat transfer coefficient. But it's really hidden in the equations. So we can use several methods, going from very easy statistical methods to very advanced system identification methods. And I show you some results for the Gainsbury case, where you see here the different methods that have been used with different measurement periods. So the magnitude of the dot gives the time that has been used, the monitoring time actually. So the larger the dot, it means we make use of more data in time. The smaller the dot, the less. And the gray bars you see gives us the uncertainty of the outcome. So this way we can, it seems possible to get a grip on the heat loss coefficient of this building without knowing actually anything about the way it is constructed. So to conclude, there are definitely different techniques that can be applied to assess the operational performance of a building. And we are quite sure if we want to do better than we are doing nowadays, then we have to go to operational performance and not design performance. That's the first step, but we have to go much further. The methods differ in input data and accuracy of output data, and there still remain several questions to be answered, but that's why we are running this project. So I hope to give more results in due time. Thank you very much.